Hello and welcome. This is the first video lecture on organic spectroscopy, and that too a question answer discussion of the previous net gate questions. We shall start this process of organic spectroscopy from now onwards in a regular basis. Today, we'll be discussing a few recent net get questions for the graduate level, and in India it is called the postgraduate level students. And I am S.S. Tripathi, formerly faculty member of Ravensa University, chemistry department, and my subject of teaching was spectroscopy, and I am delivering this series of spectroscopy lectures for the benefit of the students of all the universities of India, particularly Odisha, India, as well as abroad. Now, the channel that I am in is the SST chemistry channel, through which I will be producing these useful videos for you. So today's program will be about 5-6 problems, and make sure that if you are not familiar with the spectroscopies like IR, NMR, then stop watching this video. Maybe for in a later time you will be interested to watch. If you have already passed or crossed PG2, then it will be definitely a refreshing exercise for you. This is the GATE 2021 problem. An MCQ type of problem is very easy. An organic compound gives M plus 2, M plus 4 peaks in the ratio 1:2:1 in the mass spectrum, and shows a singlet at 7.49 ppm in proton NMR in CDCl3 solvent. And what is the compound out of the 4 choices? 1,4-dichlorobenzene, 1,4-dibromobenzene, 1,2-dibromobenzene, and 1,2-dichlorobenzene. Now, the first thing is to solve these types of problems in a very short time, because in the net gate examination you are getting a large number of questions. So you can't afford a long time to answer these questions. Maybe a minute will be enough for tackling such type of problems. And from time to time, I will be discussing these different types of problems that are set in India and elsewhere in the developed nations like US, UK, and others, for the benefit of the entire chemistry fraternity. Now, first, whether it is dichloro or dibromo. Obviously, we know that if you have a chlorine or bromine, or 2 chlorine, 2 bromine, then each such isotope has a larger isotope. For example, chlorine 35, 37 in the natural abundance ratio 3:1. But bromine, the elder sister, 79, 81 are in the ratio 1:1. And you can get the intensity of M plus 2, M plus 4, M plus 6 by expanding this A plus B to the power N. N is the number of halogen atoms of a particular type. For example, and AB are the relative abundance. the most abundant isotope, the least abundant isotope. For example, it is bromine A and B is 1 is to 1. First you expand, supposing there are 2 bromine, otherwise you don't expect M plus 4 peak. If there is only 1 bromine, then you will, at the most you will expect M plus 2 peak. But if there are 2 bromine atoms, so the presence of 2 bromine atoms, both 81 in a molecule, may be less in probability, but it is there. So you expect M plus 4 peak also. There are 3 bromine atoms, then in addition to expect M plus 2, M plus 4, you also expect M plus 6. So this is for the 2 isotopes, A plus B, right? That is valid for chlorine and bromine, which are diisotopic. N is the number of such type. How many bromine atoms are there? If it is 3, then you have to make the power 3. It will be a cubic expression. But here it is a quadratic expression, a square plus 2ab plus b square, and putting 7981 ratio 1 is to 1. This is 1 square, 2ab means 2, 1 square, 1. So 1 is to 2 is to 1. This is the intensity of M peak. This is M plus 2 peak, and this is M plus 4 peak if there are 2 bromine atoms. But had there been 2 chlorine atoms, then this will be 3 is to 1. 3 square, 9. 2 into 3 into 1, 6. 1 square, 1. It would have come in the ratio 9 is to 6 is to 1. But in our case, in the given problem, it is coming 1 is to 2 is to 1. This is the M peak. If it is 100%, then the M plus 2 peak will be 200%. The probability of having 1 bromine in a molecule having 2 bromine atoms is 2 times greater. And the M plus 4 peak will be similar to the M peak. So that unequivocally, without any doubt, says that we have 2 bromine atoms. So we eliminate these 2 possibilities in our problem. This is ruled out. This is ruled out. We have 2 bromine atoms. So whether we have para dibromo or ortho dibromo, that will be indicated, if it is para dibromo, all these 4 hydrogen atoms are equivalent. These 2 are interchangeable by symmetry operation. So also these 2. These 2 also are interchangeable. So also these 2 by mirror plane. So all the 4 atoms have identical chemical environment, and they will give a sharp singlet, 4 proton singlet. Now you are getting a singlet. But if it is a ortho dibromo, you have 2 non-equivalent sets, A, ortho to both, and this is B, but they are not magnetically equivalent. So A dash, B dash system. So they will give you 2 proton peaks. We will not discuss more because during my lectures, which will be half an hour max, we will be discussing so many versatile aspects of the spectroscopy problems that are set in the examination. But after some time, I am glad to inform you, because this is the debut making video for such stage, for the PG stage, that our group will be shortly publishing a textbook with large number of problems, workout problems with spectra and without spectra, and their solutions maybe in this year. So I will be involved in having a video series in all these spectroscopies, and more vigorously in MR, because that is the most widely advancing, studied, applied spectroscopies. Of course, we can't underestimate the importance of mass spectrometry and IR, spectrometry. Maybe the importance of UV spectrometry has been little less, but the other three are very important for characterizing or identifying the organic compounds. Now, now within a minute you can answer this is this, because there is only one singlet. So there is no doubt about it. Let's go to the second one. The second one from the same GATE 2021, the number of signals in the proton NMR spectrum of the following compound recorded at 25 degrees Celsius in CdCl3 solvent is dash. This is an integer type question. Now, from your common sense that these two protons are equivalent, they enjoy the same chemical environment, ortho to this acetyl group and also ortho to this acetyl group. So this is a A2 system. So these two give a sharp singlet. And these two methyl groups are identical. Not this one, because they are ortho to bromine. So this is B2. Now this is another non-equivalent proton being para. This acetyl is para to this bromine. So how many signals you are expecting in the proton NMR? This is 1, this is 2, this is 3. This will be a singlet. And this will be singlet, 6 proton singlet at most downfield region, maybe more than 3 because it is close to bromine. This will be 2.5 or 2.6 because it is farther away from bromine, between 2 to 3. And this will be in the aromatic region from 7 to 8. And you can find out by using the correlation table what is the predicted value. So we are not bothered about that in this question. So the answer is 3. This is A, this is C. I have given different letters here. So doesn't matter. You get 3 signals. Coming to 2020 GATE question, you have a large number of data, but make sure that you use the minimum data to answer correctly. Because it's not a identification question, it is a choice out of multiple 4 choices. So, the compound, C10S12O2, you are not required to find the DBE, double bond equivalent carbon minus hydrogen by 2, minus halogen by 2, plus nitrogen by 2, plus 1. It's not needed at all. So a strong IR band in the region of 17-20 centimeter inverse indicates a carbonyl group. A mass spectrum shows a strong peak at 1, 2, 2, and the following proton NMR: 8 2 proton multiplet, 7.6 1 proton multiplet, 7.5 to 7.3 you have a triplet, 2 protons. So from this 2 plus 1 plus 2, 5 protons in the aromatic region, because these are the aromatic regions 7 to 8. So once we count there are 5 protons in the aromatic region, undoubtedly it is a monosubstituted benzene, it's not disubstituted, right? So there is a disubstituted here. So this immediately in the question paper you rule out the possibility of these two. These have 4 hydrogen atoms, and that too in this compound these two are equivalent, 2 proton peaks. Anyway, there are 4 altogether, 4, but here 5 protons, and these two are equivalent. HA dash. These two are equivalents. A we call it B and B dash. And this is HC. So this also is the same, but so there is a tussle between C and D. And then you start looking at the other one. After exhausting the aromatic peaks, then you start looking at the non-aromatic proton peaks. You are getting a sextate. Sextate is possible only when there is a propyl group, because this CH2 will have 5 neighboring protons and give a sextate. Therefore, this is ruled out. This will never give you a sextate. This will be a quartet. This will be a this will be a quartet. This will be a triplet, and this will be a singlet. So immediately you tick this one and go to the next question. But for me, I'm interested to revise some of your study on NMR. So I have given a greater explanation, a detailed explanation that there cannot be any COOH because there is no peak, broad peak centering around 3000 centimeter inverse, and 720 centimeter is a carbonyl group bonded to benzene ring, and it is an ester, no carboxylic acid. Usually aliphatic ester is 1760, 50. So because of aromatic, the ester group is being bit reduced to 1720. So we cannot expect aromatic ketone with 2 oxygen atoms. So everything is set for explanation to waste your time, but you already have done in your examination and proceeded to the next. And the only thing missing in the IR here is another 1100 to 1200 centimeter inverse peak to confirm ester, the CO stretching vibration. It's not given, doesn't matter. We have other supporting data to rule out the 3 other possibilities and pick up one. So then we have assigned here that the triplet at 1 must be this methyl one, the sextate at 1.8 must be the CH2, middle CH2, and this CH2 bonded to oxygen will be most desilted among the aliphatic region, 4.3 triplet. And I have also assigned the proton peaks here 8 because this is close to a carbonyl group. These two will remain in the desilting region, cone of this carbonyl group. So aromatic region added to the desilting effect of the carbonyl group, the carboxyl group, makes it 8. These two are identical, and that will give a complex multiplet. So because there will be a J3 coupling as well as a J3 coupling and maybe J5 coupling. So it will be a complex multiplet. And A dash are identical chemically equivalent protons that do not couple with each other. Similarly, the next one is the triplet, because this will be only the 2 J3 coupling to give you the triplet, and the J5 will be very little, but if that will be there, then it will be a, you can call it a triplet or doublet, but here we have given a multiplet for each, doesn't matter, but you can explain. And this HB is the most, the least desilted in the uphill region, in the aromatic region is 7.6. Oh, I'm sorry. This is in between. This is 7.6 because this is para. This electron withdrawing effect, resonance effect is experienced ortho and para. More at the ortho because of the cone, the desilting cone of the carbonyl ring, anisotropy. And this is again resonance. So this is 7.6, which is the second one after 8. 1 proton. this is 2 proton, this is 2 proton, and this will be a triplet for the J3 coupling, and again a triplet, J4 coupling. A triplet of triplet will be a 1 proton TT. In all these cases, it has given multiplet, right? Doesn't matter. But I was interested to tell you, although it is not needed in this question to prove that 122 is one of the major picks in this compound to eliminate the possibility of, this one and accept this one. Because on McLaporte rearrangement of this one, which we selected, that will give you, the loss of propene will give you this one, which is having mass 122. To confirm that this is not this one, this is not, this one, there is a competition between C and D, this is not this one. We have already done. We have moved ahead because there is no sextet peak here, but still this won't give you a McLaporte rearrangement, alpha, beta, gamma. Even if there is a loss of ethylene, it will not give you the 1, 2, 2 peak. So in all ways we proved that C is the correct answer. This is the propyl, N-propyl benzoate. Let us move to the next one. How are you feeling? If you are a novice, a PG1, or you have no access to the NMR, my words might be sounding little weird for you, but never mind. This is the beginning of our program. I will be making videos from the undergraduate level to the PG and research level in a very systematic manner, and I am now from now onwards will be spreading a message through you that the youngsters, be ready. My video series and the book, our group that we will publish, will be flashed in a national and international basis if the Almighty desires, in a short period of time. Now this is GATE 2020. I think we are almost heading towards the end of our today's program. That will be a half an hour program. This is a numerical type of problem. It's a very interesting problem. In an NMR spectrometer operating at a magnetic field strength of 16.45 Tesla, the resonance frequency or the Larmor frequency in megahertz rounded off to 1 decimal place of fluorine 19 nucleus is dash. Again, it is an integer based question. The G factor of fluorine 19 is 5.255, and the beta-n, I'll tell you what is beta-n, that is a constant, it's 5.05 into 10 to the power negative 27 joules per Tesla. And H is our favorite Planck's constant. Now the field strength is given and the nucleus is given. It is a spin half nucleus, as you know, like proton, like carbon 13, like phosphorus 31. Fluorine 19 is also a very easy to handle nucleus, and its resonance frequency at a particular external magnetic field is little less than the proton's requirement, a little less than the proton. In this high field strength, such a high field strength, what will be the resonance frequency needed for a fluorine absorption? Right? Now, let me remind you from the very basic concepts of NMR that the magnetic nucleus, which has a non-zero I spin number, that magnetic moment, the magnetic dipole moment is given by this basic equation. You must remember. I will be putting, for your benefit, a PDF file carrying all these materials in the description box, and you can do that. Now, of course, you can find these in a textbook like Silverstein, Basler, William Kemp, and many others. And our book is also on the way. And I'm sorry. So this is GS, the G factor. That is a constant for each nucleus. It will be given to you. I'm not discussing any further detail about the G factor. This is Mi, the magnetic quantum number, and for spin half nucleus like fluorine 19, proton, it is half. Simply the spin, nuclear spin, because half plus half minus half are the only two possibilities of the magnetic quantum number. So for spin half, C13, proton, fluorine 19, this is simply I, spin number. And this is a constant called the nuclear magneton, beta n, whose value is given to you. And for your benefit, let me tell you, beta n, just like for electron moment, it is Bohr magneton. For the nucleus magnetic moment, it is nuclear magneton, and its value is EH by 2 pi. This is the mass of the proton, not the electron. And on calculation, E is the charge of the proton, which is same as that for electron. S is the Planck's constant, M is the mass of the proton, and that gives you a value which is called beta n, the nuclear magneton. That is the unit of the magnetic moment, joules per Tesla. But this has to be multiplied. This is 1 beta n, or 1 nuclear magneton is this much joules per Tesla. So this many nuclear magneton means you have to multiply by beta n. So value is, fortunately, you are given directly. You can apply this value. I'm just explaining what is beta n. Now GS is the G factor given. Mi is half for fluorine 19. So let us calculate. This is the G factor, 5.255. That is a non-unit. G factor is called a non-unit magnetic moment. Without any unit, it is just a unit. Once you multiply with the magnetic quantum number and the nuclear magneton, then that becomes the actual magnetic moment in joules per Tesla. But it is a unitless. I was missing that particular term. That the G factor is sometimes called unitless magnetic moment, 5.255 for the fluorine 19 nucleus. And finally, we got this value, 13.26, 10 power negative 27. And you know the basic NMR equation, the Larmor frequency is gamma H0 H naught by 2 pi. Or sometimes it is called B naught, the external field. Gamma is the magnetogyric ratio or gyromagnetic ratio. And gamma once again is related to the magnetic moment and the magnetic quantum number. In this case, it is I, spin half, it is I. So putting this gamma value here, our NMR equation is reduced. 2 pi get cancelled, because this is gamma is 2 pi mu h by mi. So 2 pi get cancelled, becomes mu h naught or b naught by h I or HMI. So putting these values, mu, we have already found out in joules per Tesla. The field is given in the question, 16.45. And H is the Planck's constant, and Mi is half for fluorine 19, and you are getting 658.7 into 10 power positive 6 hertz, means 658.7 megahertz. And had it been a proton, the G factor would have been little more, and the corresponding resonance frequency would have been little more, maybe 700, just I'm guessing. And that depends on the G factor, everything. And of course, half will remain the same, but the G factor will determine in the same field strength of 16.45 Tesla, the fluorine requires this one, and maybe proton will require 700. You can calculate that. Now this is the last one. This is a NAT 2019. You know how quickly we can answer this question in a flash, and then you go to the next question. But I will take a little more to revise. The structure of the compound, which displays the following spectra, in IR 1690. And here, very fortunately, this speaks of the ester, the CO stretching. And it seems to me that if it goes down 1700, then it can't be an ester, it has to be a ketone. Ester, aromatic ester, benzoic acid esters will remain above 1700. When you solve large number of questions, you will get a feel and experience that yes, no, it can't go below 1700. So I suspect it to be a ketone. Forget it, because everything you can't take it as granted. There is large number of effects which can alter the expected values. Now look to the proton NMR. This is 2.8, 3 proton singlet, 3.8, 3 proton singlet, 6.9. Now the aromatic region is a doublet with a coupling constant 8 Hz, 2 proton, and another 7.8, again 2 proton, same coupling constant and same doublet, but 2 plus 2 makes 4. So since there are 4 aromatic protons, it has to be di-substituted. Immediately you get it. Now you have suspected it to be a ketone or maybe an ester because the formula is not given, but in all these compounds you have given esters. Now ketones and ester, this is an ester, ketone, ketone, right? Now what is the fun of giving NMR, carbon 13 NMR? Just to count the number of peaks in the decoupled NMR spectrum, 1, 2, 3, 4, 5, 6, 7. Now can you tell me these 3 compounds give how many non-equivalent carbon resonances? I tell you, it is 7. 1 for this carbon, 1 for the other quaternary carbon at the downfield region, 2, 3 quaternary carbon, then these 2 orthoprotons are equivalent, chemically equivalent. So 3, 1, 2, 3, 4, this equivalent, 5, 6, 7. In all these para-substituted compounds, you will find 7 carbon resonances. So you are really getting 7. But here in ortho, all these carbon atoms are non-equivalent. 1, 2, 3, 4, 5, 6, 7, 8, 9. We are not getting 9 carbon resonances, 7. So the possibility of this, the D, is ruled out. This is ruled out. This is 9 carbon peaks. But all this 7 carbon peaks. But out of these 3, you have to eliminate now without going to the next phase. Now see. If you are little, conversant, then this 3.8, 3 proton singlet has to be the methyl group bonded to O. So here there is no such thing where a methyl group, as it is properly pronounced, methyl group is not bonded to O here, so this is ruled out. Here, then the competition between B and C. Here, this can be 3.8, it is bonded to O, and this can be 3.8, can be bonded to O. Now, how to eliminate the one and take the other between B and C? Now, my suspicion was it is a ketone. Had it been a benzoic acid ester, it would not have come down 1700. This is my suspect. And now, if this is the case, then the methyl bonded to carbonyl will be 2.2, 2.3, and if it is aromatic, it will be more, and we can assign this 2.8 peak to this one, and this is 3.8. Now, if this is a methyl bonded to benzene ring, it cannot cross 2.2. You can look to the periodic table and take it from me now that any methyl group or methylene group bonded to the benzene, directly bonded to benzene, cannot go beyond 4.2 or 2.3. So the large distilled 2.8 definitely puts me into a strong conviction that this is ruled out. First suspicion was 1690 to be a ketone, not an ester. The second suspicion is this cannot be 2.8. No, not possible. So this can be 2.8. It is usually 2.2, but aromatic makes it 2.8. But this is already aromatic. So you can find in the correlation table, it is 2 to 2.2 or 2.3. Cannot go beyond that. And most importantly, the here, of course, had I been the examiner, I would have given, question setter, I would have given a mass spectral data. That is not given. So only this is the consideration to cancel this and take this, because the aromatic CH3 cannot go up to that extent, and aromatic ester cannot go below 1700. These are the two considerations which, and I would have given that the base peak is 135. Then if it is a ketone, the alpha cleavage, the CC bond next to the heteroatom, that gives you the base peak. The loss of 15 methyl radical give you this peak, which is 135. But had you taken this one, then this loss of methoxy would have given a different M by E peak, not the 135 peak. So I have solved all this, and I have tried to, the answer is B. This answer is B. I have tried to solve, I have already crossed 30 minutes. I'm sorry for that. It is 5 minutes past 30 minutes. I will close very soon. Now, I have given you the assignment, but just for your memory, just for your revision, for refreshing your memory, that this is 2.8. And what about the proton peaks, aromatic proton peaks? There were 2 proton, 7.8. It must be close to the desilting acetyl group, and the uphill peak 6.9 should be close to the plus R or plus M methoxy group, right? This is very understandable. And each one will be a doublet. By J3 coupling, the J5 is invisible. So this is a doublet, this is a doublet, and the equivalent protons, they do not spin couple. So each is a doublet. The J5 is not visible. So J5, it's not J4. I have wrongly written here J5, because this J3 and there is no proton here. 1, 2, 3, 4, 5. J5 is 0 here. It is a A2 X2 system. A2 X2 system. But since J5 is 0, you are getting a doublet of each type. So I have assigned the carbon resonances. This is 26. You can just wait, our book will be coming. You can, the teacher of all teachers, the master of all masters, I have seen in coveted institutes like Massachusetts Institute, MIT, in California Institute of Technology, and everywhere, even in US, the standard book of reference in the graduate courses is Silverstein and Basler. Silverstein and Basler is the Bible, the Quran, the Bhagavad Gita of spectroscopy, and my hats off to the great master, Silverstein. And now there are so many co-authors. So with that, I have, this has to be 165 peak. This is 197 is the carbonyl carbon, much desilted carbon 197, right? And these are the aromatic. Out of this has to be, you can find that alkoxy group will produce a large desilting effect to the ipso carbon 30, and also this one will produce some 2 or 3. So altogether it will be 128 for neat benzene. So you will be finding the maximum desilting occurs here. It's not by plus M, it is by minus I effect. It is desilted here, and this is by the resonance effect desilted here. So they are added up 165. And you will find that this carbon is 129. The prediction is almost 100% matching with the actual value given in the data. 130 for these two equivalent protons and 114 for these two equivalent protons. That's the end of today's program. Thank you so much for a patient hearing. And if you are a PG student in India, or you are a graduate or undergraduate student in elsewhere in the globe, please share this with your friends who are going to be benefited from this discussion, and also say that we are coming on a regular basis to discuss on organic spectroscopy, which is our subject of interest. Bye bye. Let me know your feedback in the description box, and if not subscribe to my channel, don't hesitate to do so, and also the ring button, and also the like button if you have really liked it. I have not told that in the beginning, I'm telling at the end. Many would have escaped after a few minutes. So bye, see you soon for the next video.